Hello, my name is Dongju Seo, who the first author of this paper. This work is supported by UC Irvine and Kookmin University from Korea. So this presentation sequence is that I will talk about the introductions for your understanding of this paper, and then I will tell you the motivation what is solved. After that, I will talk about the dynamic iFogSim, what we made. In last, I will summarize it. Let's talk about the introductions first. As you guys know, the Internet of Things systems highly draws attention these days because iOS devices like a smartwatch and mobile can run the various and powerful applications on the system. Definitely, IoT systems need a comprehensive solution for dealing these various IoT applications. So one of them is resource management solution. Users who using the IoT system usually want to get a nice experience from them. For that, flexible resource management policies needed in this region. So for solving complex problem on the IoT system, the fog paradigm became known to the research region. Fog paradigm is simple, like right picture in this slide. Just put a manage law to the device between traditional edge and cloud devices. The traditional cloud edge system's problem is that each layer's difference of hardware resources is too high. To fill this gap, fog paradigm can buffer up between the edge and cloud and take some works for the both layers. Let's think about the researcher and engineer who aim in resource management. They need to manage the resource in the each device efficiently. But if they try to build a layered system in the real world, then they face lots of physical constraints like buying devices and network and so on. So they need to use simulation tools that spans these multiple abstraction layers. So from this needs, already lots of simulators in this research region. These fog system simulators have two big problems. First one is that it cannot run the real-world application. Only one simulator, DockerSim, can run the real application on the simulator, but its scheduling is highly dependent on the Docker, so they cannot manage their virtual device only. All of other focus simulators only support virtual application. It means that it cannot support the concurrencies of operating systems. Most of the simulator only can run the system with sequentially. Even some simulator can support it, but they have their simple workload scheduler, like time-based or work size-based. So we want to run the real-world application on the fog system simulator on the virtual devices. And second problem is that they don't care about the virtual devices. They only configure the virtual devices by using the number. So their power consumption and computing power metrics is come from numerical calculation. We know every simulator is come from numerical calculation, but we want to more real-like behavior of the virtual devices in the simulator. So we motivated by Lex simulator capable of supporting a full stack communication computation co-simulation. So we decided to build platform by using excited simulators and some source codes for making them. And also we need a system's behavior change during runtime. Below red box is our contribution summary in this paper. We propose a framework which is able to simulate an IoT system in full stack simulation mode. And we add a cross-layer controller module to the framework to be able to dynamically control the system. So now let's talk about the framework what we made. This framework is composed with 6 main components. SniperSim is first of them. We didn't any modify to this original SniperSim. It's a high-speed and accurate x86 multi-core simulator, and it can generate instruction per second, and power consumption, and other device statistics for simulated devices. This component helps us to simulate the virtual device in the platform. Second one is extended iFogSim. Original iFogSim is one of the most famous simulator in this field. It can simulate layered system with lots of parameters, but it don't have any handy interfaces. For example, if we want to change the number of edge devices in the simulator, then we need to change the source code, not an input file or configuration file. So we made a handy interface for the iFogSim by using text input and adding TCP predictive network model to the iFogSim too. Why we added TCP network model to the iFogSim is that current iFogSim's network interfaces is simple linear calculation. So we added the TCP network model referred from last cited paper, and its result is not bad. Using this extended iFogSim, we can simulate the workflow and network packing logs between virtual devices. Third and fourth components of dynamic iFogSim is configuration components. This platform needs to configure lots of things, so core simulation environment and system configuration can configure the virtual devices configuration and virtual layers one too, so they can passing to these configuration to the all components too. And last one is that system cross-layer controller. These components can coordinating all components in the framework, so it can handle to the sniper simulator's result and extended iFox's result too. And finally, it can make the result from the two simulator for us. So basic workflow of this platform is like this. In first, user prepare the system configuration for the extended iFogSim, SniperSim, and applications for running in the SniperSim 2. And after that, in second, core simulation environment can send these config to the simulators and prepare the platform to run the whole simulation. Whole simulation means that workflow of virtual devices and each devices too. In last, system cross-layer controllers start to the whole simulation with other simulators and getting the result from them. For example, if a user want to check with some Python application on them, then system cross-layer controller run the iFogSim first with the network and the workflow configuration, and then sometime virtual device in the iFogSim face the unknown application status what usually went in there then. Controller sent to the Sniper simulator for checking the application's running time and power consumption with the current status of the virtual devices. Finally, controller passed the result of Sniper Sim, the extended iFogSim can continue the simulation. So this is basic workflow of this platform. Now I will move to the application case study. We use the fall detection application. Simply talk about this application. It can extract a feature from accelerometer signals. It's a Python file and it includes 6 steps for feature extraction. So for simulating this one, we're supposed to define two-layer edge and fog. First layer edge have a sensor node too. It can periodically transmitting the data to the edge node, and edge node can send the data to the fog layer, and after that fog layer compute and return the response to the edge. So it's basically 3 devices on the our scenario, sensor and edge and fog, and they can send the data between by using the network model what we added to the extended iFogSim. That is our scenario of this application on the virtual devices. An IoT system's behavior dramatically changes over time due to variation in environment and system parameters. For example, uncertainty can lead to the variation in total response time and energy consumption. In addition, any robust system must dramatically adapt to the actual optimal quality of service. So this is the result of our scenario. Upper right table is virtual device specification. Below graph can show the F1 score with the response time. F1 score means that the accuracy of the model. Our feature extraction application have one parameter called the window size, and it can make a model by using that value. So we explore window size of the fire detection application 1 to 50 and try to find the optimal value in these virtual systems layers with the virtual devices and virtual network too. And we can see the frequencies of the virtual devices can affect to the F1 score and response time, even energy consumption too. Let's see in the first graph, we can see 7.6 seconds with the 0.69 F1 score is really looks so nice in an accurate, but it's not fast and efficient. As you can see in these graphs, finding the optimal value for the application in the IoT system is really hard because lots of factors can highly affect to the each application's response time. Even they change the application's value like a window size in the application, then workflow or any factor in this platform can affect to the that application's response time. So we can show the that kinds of problem in this platform, and this platform can help to the researcher for their research. In last, we can also see the packing loss can affect to the whole system's result too. It's a graph of response time. WS means the window size. So if we assume that we have a response time deadline for the application, then this system have to move like a lead line dynamically. Our platform's controller can support this dynamically. So for that, our controller include the brute force agent for making decision by packing laws and any system parameter from the virtual devices and virtual workflows. It can make a decision at the time when the platform needed. So user can make any agent to the platform too. So let's summary of our contributions. We made a full stack layer system simulating with the application source code, and it can dynamically control the whole system. In last, we added case study in our paper, and all of them open in the GitHub too. So conclusion is that this paper presents the first full stack Internet of Things simulation framework. As I mentioned before, exciting solutions lack dynamism during the runtime, but we also supported this dynamism during the runtime too. And we demonstrate the capabilities of our framework using a healthcare IoT-based application too. But we have a to-do list in here. We have to support the multi-threading application in the Sniper Sim. And as you guys know, recently IoT system is almost running on the ARM architecture system. So we plan to support the ARM system simulator into this platform too. And now we have only brute force agent for dynamism control in the controller, but we plan to implement another agent policy for primary decision in the dynamic iFogSim. Thank you for listening this presentation. And please using this platform for your research and feel free to tell me whenever if you need any question, any help about this platform. Thank you.